Okay, so first, the only real new thing that I have for you is that we're going to keep reading in the book. So today we're going to be talking about the layers of the atmosphere, and on Tuesday we're going to get into some different kinds of pollution. So I'd like you to be reading 2.8 through 2.10 in preparation for that. We are going to be doing something in class that is an assignment that you should be done with it before you leave class. But I don't think, other than just the ongoing, you do have videos for chapter 2, you do have guided notes that eventually are going to be due. Other than those couple of things, I don't have anything new. So any questions? Okay, so first thing I have, separate these. I have some guided notes. These are not the guided notes, but just the important things that I want you to get out of class today. Because I'm going to be saying a lot of things, some things that it's like, this might be interesting, some things that it's like tangentially important, but this stuff is the stuff I really want to make sure that you know what it is or how to work with it. So I'm going to pass this around, and then as we go through the lecture today, then you'll know the things to focus on. You are welcome and encouraged to write more. Okay, so on Tuesday, we talked about the composition of the atmosphere. We also talked about interpreting pie graphs. So the first thing on your notes there is, I do want you to remember what are the percents for each of the 4 most common gases. So anything other than other. If you don't have that in your notes, make sure that you write that down as something to remember. So nitrogen makes up most of our atmosphere. That's almost 80%, and oxygen is a little over 20%. And then argon is about 1%. Now, to me on this graph here, it kind of looks like argon and carbon dioxide look like they're about the same size. Really, carbon dioxide is just a tiny portion of that. It would be like 1/20th the width of the green argon section there. So that was what I was saying about if you have teeny tiny percents, then they almost disappear. They're so small on a pie graph. So those are our major composition. When we add water to the mixture, if we have humidity, relatively these stay the same to one another. So nitrogen is about 4 times as much as oxygen, and it's always going to be roughly 4 times as much as oxygen. But as you add humidity, then everything else becomes just a tiny bit smaller in order to work that water in there. So it might be oxygen is actually 20 and nitrogen is actually 77 or something like that. So water, can be almost absent, so less than 1%, or it can be up to like 5% in the atmosphere, depending on where you are, depending on what the weather is, depending on the time of day. It's actually pretty unusual to have very dry environments. So between here and Lexington is the Center for Applied Energy Research, and one of the things that they do is they work with batteries. And in order to work with batteries, you remember when we had the lithium and we put it in the water, it was very, very reactive. It was fizzing and popping and bubbling and stuff. So they have to have super, super dry rooms. And so if you visit the facility and they let you into that room, even just a few minutes in there, you can feel like your skin's starting to feel crinkly, and like your nose is starting, like the membranes inside your nose that are usually moist start to dry out a little bit. And so they say that the people that work in there, they can't work in there for 8 hours a day. They have to come out every hour or so in order to let their body have a little bit more humidity. So even in very dry places, there's usually some water in the atmosphere. Okay, so these are the percentages of our 4 most common gases. And we're going to come back to that last column when we start talking about other ways of measuring concentration. But before we do that, I'm quickly going to go through this. We talked about this on Tuesday. I'm not going to pause on these, but how did these gases get here? Volcanoes came up with most of the nitrogen that reacted the ammonia to form nitrogen and hydrogen. We said photosynthesis is what helps us get the oxygen in the atmosphere, and we have this kind of steady trade-off of photosynthesis and respiration. There are far fewer animals than plants, but plants do both. So they put out a lot more oxygen than they take in carbon dioxide, but they use carbon dioxide the same way we do in order to make their food, or in order to do their cell processes rather. And then we said that for the potassium, there's these nuclear reactions that go on. You don't need to know what the nuclear reactions are, but they basically, the potassium turns into argon, and that's how argon ends up in the atmosphere. Okay, so inhaled versus exhaled air. One real common misconception is, oh, I breathe in air and I breathe out carbon dioxide. So the only thing coming out is carbon dioxide. That's actually not true. So if you think about somebody doing CPR, it wouldn't be very good to do CPR if you're mostly putting carbon dioxide in that person, right? So you still have to have some oxygen in there. And the nitrogen doesn't really do much at all. So the nitrogen pretty much stays the same. So it's still 78%. But some of the oxygen gets converted to carbon dioxide. So we go from 21% to 16% for the carbon dioxide, or for the oxygen. And then that percentage of the carbon dioxide goes up to about 4%. So yes, if you were doing CPR, you're giving that person some carbon dioxide, but you're giving them much more oxygen. So it's more important that, oops, we did that suddenly. It's much more important that we get that oxygen to them. So just want you to recognize that even when we exhale, while the carbon dioxide increases quite a lot, it's still a small percentage of what we're breathing out. So one of the questions that I like to ask on a quiz or a test is, when you breathe out in the air that you exhale, what is the most common gas? What is the most abundant gas? And it's still nitrogen, just like when you breathed it in. Okay, questions on this? Okay.
Sorry.
Yes.
Question to it's how do they change?
So I would just say that oxygen goes down and carbon dioxide goes up. Yes. Oh, you didn't get one? Sorry. I thought I had. Anybody else not get one? Thought I had a lot left over. Okay, so there are clearly other things in the atmosphere. There was that tiny little sliver on the pie graph that said other gases. And we know that some other things are in the air, in part because we can smell them. So this is one of the chemicals that can be found in coffee that has an aroma that is very identifiable. Bananas have a very distinctive aroma, so you can smell that. And then this is methylbutyrate, which has kind of a smell of butter. So we can tell some of these smells, even though there's still teeny tiny portions in the atmosphere. And so that's really helpful, as you might want to detect if there were a fire in your home, or you might want to come downstairs when the cookies come out of the oven because, hey, fresh hot cookies, who doesn't love that? So being able to detect things in small amounts is really important. But some things can harm us in really small amounts. So even if we're not worried about a fire, some of these other chemicals here, dihydrogen sulfide, the two hydrogens and the sulfur there, that's extremely toxic. And we can smell that in very small amounts, fortunately, so that we can be aware to remove ourselves from that situation. That's the smell of rotten eggs. So the chemicals that come off of rotten eggs are not enough to poison you, but it is enough to alert you that that smell is there. So if you were in the lab, the chemistry lab, and you smelled that, probably we don't have rotten eggs in there. That's more likely to be a chemical that would harm you. So you would say, I should not be in this situation. Let's see, up on the top, there is a nitrogen dioxide. So that's one of the pollutants that we will talk about that can get into the atmosphere, and that can be very bad for your lungs. It can lead to acid rain. And then at the bottom, three oxygens together is a chemical called ozone. You've probably heard of the ozone layer. And in the next chapter, we'll talk about how it has both good things that it does and bad things that it does. But in this chapter, we'll kind of focus on why we don't want to be breathing it. So we want to be able to detect these in very, very small amounts, which means percents aren't necessarily going to be the best way to go. So again, we have the composition here on the left-hand side, but when we want to measure something that's in a much smaller concentration, we might use parts per thousand, parts per million, or parts per billion. So a percent is the same thing as a part per thousand or per hundred. So a cent is 1/100th of a dollar. A century is 100 years. So per cent means for every 100. So for something like carbon dioxide, it a lot of time is reported as parts per thousand because it is such a small percentage. And then things that are extremely toxic, we don't want to wait until it gets into the parts per thousands. So we start reporting it at parts per million or parts per billion. So sometimes you will see these as PPT, PPM, and PPB. The next level after parts per billion is parts per trillion, which would also be PPT. So sometimes people just say out parts per thousand or parts per trillion, so you don't confuse the two. Okay, so what we're going to do is look at how can we go between a percent, which is a really small number, to one of these other measurements. So at the top left here, I have several symbols in a row. So we've got our percent, and then a T for thousand, and then just two dots to mark place values, and then M for million, two dots, B for billion, two dots, and then TR for trillion. We won't go into the trillions. That's just where it's at. So if I want to go from a percent to parts per, I'm going to count how many places I move over in order to get it. So it's just one place to go from a percent to parts per thousand. If that's what I'm doing, then I'm going to move my decimal point that far. So if I look at, oops, I deleted the first thing. If I'm looking at argon, I think that was the first one on there. So that was 0.93%, right? To go from percent to parts per thousand, I just move the decimal point by one because thousand is 1 over from percent. So it would be 9.3 parts per thousand. Now, if I wanted to go from percent to million, how many places over is that? So there's the T, the two dots, and then the M. So that's 4 places. So that's why we put the dots in there so we don't forget to count them. So if I was going to do that, I would go, oh, let me do this first. Okay, so that's what you're going to put in the chart at the top where, oh, I have parts per million there. Change that to parts per thousand on the chart. I meant to put parts per thousand. So for your argon, you would say it's 9.3 parts per thousand. Now, if we wanted to do parts per million, we would take our 0.93 and move it 1, 2, and then just add some zeros, 3, 4. So this is where the million is. So it is 9,300 or 9,300 parts per million. Okay. So I personally would rather deal with a number the size of 9.3 or 0.93 than deal with something this big. So if I have something that's as big as nearly a percent, I'd probably just leave it in a percent. But if I have something that's a really low concentration, like ozone, so ozone here, it says it is 0.00004%. I don't want to deal with a teeny tiny number like that. Like all those zeros make my eyes sort of cross. So I'm going to figure out how to go from percent to parts per billion. So it was from percent to 1,000 was 1. Then I have 2 dots. Then I have the M. Then I have 2 more dots. And then I have the B. So that's 7 places. So I'm going to move that decimal point over 7 places. And if I run out of room after the 4, I'm going to stick in zeros. So try that and see what number you come up with. So I get 40 parts per billion. Is that what you got? That's possible. I count them. Okay, so take a second for the chart you did. We did argon. So we said argon was 9.3 parts per thousand. Figure out what carbon dioxide would be in parts per thousand. So I said that was one we often report in parts per thousand. So if it's 0.043%, what would that be in parts per thousand? Yeah, 0.43. We just moved the decimal 1. And if I wanted to do parts per million, then it would be more like 430 parts per million. Okay, so questions on this? So if I put something like this on a quiz or a test, it would be like 1 question worth 1 point. So I don't want you to panic because there's, you know, all of these numbers in decimal places. Just a tiny little portion of your grade. Yeah, Jason. So the textbook says 0.041 because it was published in 2016. It has since gone up. Okay. So the other thing that I'd like you to know about these measurements is which is bigger. So if somebody said that there was a material that was 5 parts per thousand and another material that was 5 parts per million, which is more? Per thousand is more. So this says the concentration in parts per million. So parts per million is 1 here. You can't really tell the difference between 1 part per million and not having it, right? Over here, this one translates to parts per thousand. So that's like a pretty muddy looking thing. You wouldn't want to drink that kind of water. We turn out the lights so you appreciate it a little bit better. So yeah, don't want to be drinking that. Okay, so I have a couple of what are called Becker bottles. Just a second. Okay, so this one has 1 million beads in it, and there are beads of different colors. And so I'll kind of pass this one around and you can kind of look for the different things. Aside from the blue, what color do you see the most? The yellow. So the yellow particles are 100 parts per thousand. Okay, so that would be about 10 times what argon is in the atmosphere. Okay. Do you see any other colors? Red is in there. Red is about 10 parts per thousand. So the red is about the concentration that argon would be in our atmosphere. There are white particles, which you might be able to tell up close. I have yet to be able to find pink particles, but there are apparently pink particles in here. There are green ones and 1 black one in here. So that kind of shows the different concentrations. So I'll let you pass this around and kind of play with it, see what you think. This is, it's also called a Becker bottle, but this only shows 1 part per million. So there is, I'm going to leave it right here, 1 black particle. I don't think we can see it on the camera, but there's one black particle in this entire bottle. It tends to work its way to the surface. There. So only one black particle in this whole thing. And now I'll let you guys see if you can find it. Okay, so that is parts per million. If I wanted to have 1 part per billion, there would be a bottle like that, and then 999 bottles with only yellow beads. So if we filled this room with bottles with yellow beads, and that black particle was the only black particle, that would be 1 part per billion. Yes?
So parts per thousand is the big.
So parts per thousand is the biggest. Yeah. So if you think about, sometimes you say, oh, you're 1 in a million. But if you said to somebody, you're just 1 in 1,000, that's not quite as impressive as a compliment. But if you said you're 1 in a billion, that's like you're 1 out of 8 or 9 people on the planet. So that's really impressive. All right. So the other thing, and I'll keep coming back to this, is that the more dangerous pollution is, the smaller we want to put the limit on it. So for lead in our drinking water, we want that in parts per billion. The limit is like 15 parts per billion. But for something like copper, we actually use copper a little bit in our bodies and whatnot. We don't want to have it too high. The limit is in parts per million because it is much less dangerous than lead. Okay, so now we're going to talk a little bit about the atmosphere. The 2 portions of the atmosphere that I really want you to know about are the troposphere and the stratosphere. So I'm going to talk about them a little bit more. We'll talk about the thermosphere and the exosphere just a little bit. And again, I'm going to turn off the light up here so it's easier to see the graphic. Okay, so the troposphere takes up about 7 miles from the ocean surface. And so Mount Everest, how many miles high do you think Mount Everest is? 2 miles high. Anybody have another guess? 4, a little bit higher than that. About 5.5 miles high. Okay, so the troposphere covers all the mountains on the earth, right? And even the people who live in the Himalayas, where Mount Everest is, even those people don't live at the height of Mount Everest. So people all live in the troposphere. They don't even get near the top of the troposphere. Butterflies can get about 4.5 miles high. Yeah, so they can't get the top of the Mount Everest, but they can get pretty high, way higher than birds can. But bees, there is a certain kind of bee called an alpine bee. So alpine means mountainous. Bees can get up to 5.5 miles high, almost 6 miles high. So there are some bees that can get a little bit higher than the peak of Mount Everest. All right, so all people, all plants, everything that's living inside the troposphere. Also inside the troposphere is our weather. So rain, most of the clouds, any storms that would happen, those are going to be in the troposphere. So most of what you consider to be Earth is actually inside this thin first layer here. Okay. All right. What about our air molecules? Because that's what we're talking about. There are air molecules above the troposphere, so there are molecules way out even into the exosphere, but 75% of them are in the troposphere. So it's mostly squished down into there. That has a lot to do with gravity. So we have them there. The temperature tends to be warmer closer to the ground. So you may be familiar with the idea that if you go hiking in the mountains, like if you go out to Natural Bridge or Red River Gorge, that tends to be cooler there. Maybe even 10 degrees cooler there. If you were to go into the Rockies, then we have the snow-capped mountains, even in the summer, so much cooler there. And so that's because the sun heats up the earth, and the earth sort of radiates that heat up into the atmosphere. And that works through the troposphere. But by the time you get to the stratosphere, then you're far enough away from the ground that that's not really doing much heat. And so most of the heat in the stratosphere is actually coming from the sun. And so the temperature gradient shifts. So first it gets cooler as you go up, and then it starts to get warmer through the stratosphere. So the stratosphere is about 3 times as big as the troposphere. It doesn't really look like it here, but this is about 3 times as much as this is. And that's the main thing that's important there, is that is where the ozone layer
Are
is.
there any living things?
All living things are Mount Everest or below, so except the alpine bees, and they only just barely get over the peak of Mount Everest. So those are kind of the important things there. You can also see that as we move further up, we have these streaky things here. What do you think those are? Those are meteors. Okay, so I had to look this up because I always forget exactly how it works. So a meteoroid is when it's in space, and then when it starts burning and gets on fire here in the mesosphere, which is the next layer, then it becomes a meteor. And then when it hits the ground, if there's anything left over, it's a meteorite. So they're all the same thing, it's just where it happens. But here we would call it a meteor. Okay. Is that the same thing as a comet? No. So comets never really enter our atmosphere, hopefully. They glow because they get close to the sun. And so the sun starts heating up. They tend to be big blocks of ice and rock, but the sun is heating them up enough that that starts to glow. But that's way further out. All right. So as you go through the thermosphere, you are going to get different kinds of satellites. That's where you are going to find auroras. So aurora is the northern lights. That's the like pretty glowy, wavy, pink and green things that sometimes appear like Alaska, Scandinavian things. It's called the thermosphere because it's actually pretty hot. So if you can see it on here, this says 1727 degrees Celsius. For us Americans who don't know Celsius, that's about 4,500 degrees Fahrenheit. So very, very hot. But if you were hanging out on this satellite here, of course you wouldn't be able to breathe because there's not enough air up there for you to breathe. But let's say you have your oxygen tank. You would freeze to death. And why would you freeze to death if it's so hot? The temperature is measured by how fast the molecules are moving, but they transfer heat to you when they run into you, but they're so far apart, they wouldn't be running into you often enough to keep you warm. So you would be radiating heat off without the air molecules coming back and heating you up. So that's kind of an interesting paradox there. All right, and then the International Space Station is at 250 miles up. So it's partway through the thermosphere. And then beyond that is the exosphere. We consider that to be outer space. So just the moon, Pluto, galaxies far, far away. Okay, so the most important things we want to remember is where is the ozone layer and where are we? All living things, all of us, all the stuff we do, that's in the troposphere, and then the ozone layer is in the stratosphere. Okay, so I'm going to pause here, and what we're going to do is we're going to make a model of the atmosphere. So first I'm going to have you cut these out, just cut out all of the shapes. For the smaller ones, like this is the meteor, I did not cut every little corner on it, I just kind of vaguely cut it out. And then we're gonna assemble this in order. Everybody gets to do this, because this is gonna be part of your notes, and then you can use that on your quizzes.
I'm not very well.
That's okay. It's kind of secret. All right, so once you have things cut out, and I realize you're not all quite there yet, but once you have them cut out, these semicircles are going to represent different layers of the atmosphere. So you're going to label them, go from the outside in, exosphere, exo meaning exit, thermo was the hot one, meso goes right in the middle, because meso means middle, stratosphere, and then troposphere. And then, so make sure you write small enough that you can still see them. Your earth can go in the middle. All right, so we're going to end up writing on the backs of these semicircles. So if you want, if you can tape them together now, but you're going to tape them at the bottom, not at the top, so that these flaps can fold down and then write something on the back. If you'd rather wait and tape them after we've written on the back, that's fine as well. All right, so as you are assembling these, one of the things that I'd like you to write down is how many miles from the Earth's surface these are. So troposphere on average is about 7. The stratosphere, I think we had said about 23. Now these can vary a little bit. The mesosphere goes up to about 53 miles. And then the thermosphere is huge, so it kind of looks like it's just a little bit bigger than the other stuff, but we jump from 50 miles to 375 miles. Right, so you're going to want to write those down because that's going to help us figure out where everything else is. All right, so our troposphere is going to have a lot of these little pictures here. We're probably not even going to be able to fit them all with the Earth as well. With the Earth in here is going to cover them up. But what's something that's going to be in the troposphere among the pictures here?
Hot air balloon.
The hot air balloon, definitely, because people can't really survive outside of the troposphere. Anything else? Mountain, yep. Even Mount Everest is inside the troposphere. The lightning, so we said weather was inside the troposphere as well. I'm going to trim this a little bit so it doesn't cover my word. All of these things are inside the troposphere. Weather balloons kind of ride in between the troposphere and the stratosphere and the mesosphere. I thought we had a picture of a weather balloon, but I don't seem to have one unless I lost it. Do you guys have a weather balloon? Okay, so the weather balloon, if you look in the back, it says it's at 23 miles. Now, not exactly, there's going to be a range, but that's really right on the border between the stratosphere and the mesosphere. So that's the one that doesn't have the little basket for people. They just send the balloon up, no people, and it collects information. Oh, here's my. This one's going to be right on. we have two kinds of satellites. So there's one that looks like this guy, and then one that's got a tiny little space shuttle attached to it, which I seem to have lost mine in opening and closing my books. It looks like this right here. This one is the International Space Station, ISS. So on the back board, it says International Space Station is at 250 miles. So where would that be? That one's going to be in the thermosphere. This is ISS. But other satellites can be much higher. So you can put this other satellite way up in the exosphere. So we can have them go really high. And what amazes me is that these can orbit the Earth. Because remember, a satellite is something that goes around the Earth. They go around the Earth maybe every hour and a half to 2 hours. So the Earth turns around once in a day. A plane flies from, our country to another country over the course of half a day, but in less than 2 hours, these satellites can go all the way around. I find that really amazing. And do you remember where we said the meteors? Those were in the mesosphere. That's kind of easy to remember. So go start with that. All right, and then this guy is supposed to be our aurora, I think I have it upside down. It goes like this. The northern lights or the southern lights. So you might have heard it called the aurora borealis. We said that was going to be. That's going to be in the thermosphere. And then our space shuttle, this little guy on the ISS is a space shuttle, so it basically goes in the same place that the ISS does. Are there any other pieces that I missed? Like I said, we wanted these flaps so we can put information on the back of them. And the most important information is, again, going to be for those first 2 layers. But I thought it would be good to put for the thermosphere our little paradoxical thing. So what we can do is flip this down, leave the exosphere where it is. But for the thermosphere, I'm going to write in that we can have 4,500 degrees Fahrenheit, but the freeze. This is because the gas molecules are far apart. So have you ever heard the phrase, in space, no one can hear you scream? It was a tagline for the movie Alien. So why wouldn't you be able to hear somebody scream in space?
There's no air.
There's no air. So sound travels through air by the molecules hitting one another. So just like the molecules are too far apart to warm you up, they're also too far apart to conduct sound. So also in the thermosphere, no one can hear you scream, or you can say no sound. All right, for the mesosphere, and I'm putting meso on the down flip part, so I remember this is the mesosphere, not the thermosphere. This is basically where we have enough air molecules to create friction. Friction is what causes meteors to burn up. So even though we've got more air molecules there that they can rub against the meteor and cause it to blow and catch fire, it's still not enough for us to breathe. So thinking about, if you're at the top of Mount Everest, you want an oxygen tank with you because the air is so thin there that it's hard to breathe. It's about half the density there that it is on the Earth's surface. And we are miles and miles above that. So it's enough to create friction, not enough for us to breathe. Okay. So for the stratosphere, the key thing here is this is where the ozone layer is. In chapter 3, we are going to be talking about the ozone layer. So in this layer, there is enough air for jet airplanes. So jet airplanes, because they are burning fuel, they need oxygen in order to burn. And this is why we can't get jets to go any higher than this. But in the lower parts of the stratosphere, we can have some jet airplanes. All right. And then in the troposphere, this is where all life all weather occur. Storms, clouds, all of that good stuff is happening in the troposphere. This is where 75% of the air is. This tiny thin layer. Zoom that in a little bit more because I had to write pretty small. All right, so as I said, you can use this on your quizzes. I think we will probably do a quiz next week, probably on Thursday. I'm gonna kind of look over things and make sure that I post that on Canvas. We might wait until the following. All right. The next thing that we're going to do is we're going to talk about how we name molecules, because we're going to be talking about a lot of different kinds of molecules in the in the atmosphere, some of which are pollutants. And so we want to know by looking at the chemical formula what the name is, because I'll say the name rather than giving you the chemical formula. So you kind of want to know what I'm talking about. So when you're done taping things together, pull out your notes so that you have this. Does anybody still need this to kind of see where to put things? All good here? Oh, I am gonna put a link to a site. It's called Climate Kids, but I think this is really neat. Let me pull it up here. So this one shows you to scale how big things are. So you can see this is the World Trade Center, which one World Trade Center doesn't really exist anymore since 9/11. But the tallest buildings in New York are about here. And then this dotted line is showing you how high it is. So here's a blimp at 1.5 miles, and you can kind of scroll through. We've got the jet stream, which causes weather, commercial airlines. Here we're getting into the stratosphere. And then once you get up really high, you just have to scroll and scroll and scroll and scroll to get to the next thing. So that can really give you a sense of scale. I thought that was really kind of cool. Okay, going back to our PowerPoint, we are looking at naming compounds. Now we are going to look at what are called covalent compounds. So covalent compounds make molecules. So we have some compounds that make crystals like salt, and some compounds that make individual little molecules. These are made only of non-metals. So if you think back to when we were talking about the periodic table, we said that there's this diagonal line, it's these brown elements here, and to the left of them, most of the elements are going to be metals. But to the right, all of this green and blue stuff, those are non-metals. Those are the only elements allowed to be in here. Now, if it has a lot of carbon in it, there are different naming rules. We're not going to worry about those different naming rules. Those are what we call organic molecules. So we're going to see a couple of examples that follow these naming rules that happen to have carbon in them, but mostly if you see carbon, we're just going to ignore those. So we're going to be talking about binary compounds. This means there are two elements. Now, of course, you can have more than two elements. The naming rules get more complicated. We're going to stick with the ones that are just two elements. So usually it would be something and oxygen. And so the main thing is we're going to name the elements and then use some prefixes to tell us how many of those atoms are in the molecule. All right. So most of our elements that we're going to use, carbon, nitrogen, hydrogen, sulfur, oxygen, phosphorus, chlorine, those are the ones that we're going to see in these molecules. But usually if it's carbon, that's what we call organic. And so you can see these that have a lot of carbon and hydrogen, those we won't bother naming, okay? We're going to ignore those. All right. So as an example, I had showed you previously H2S. I said that was really toxic. It smells like rotten eggs. So what we would do is we would name hydrogen first because it appears in the name first, but we would put the prefix di to mean two. So dihydrogen. Now for the sulfur, there's not a number there. So in chemistry, I say the number 1 is invisible. We don't write it down because we know there's a sulfur there. We don't have to tell you how many because you know it's there. It's not like you think there's 0. So if there's no number, then it's 1 and we use mono. So we would call this dihydrogen monosulfide. if I have N2O5, then there are two nitrogens. So I say dinitrogen, and then I say pentaoxide. Sometimes we leave the A out next to the O, so we just say pentoxide. Either way is fine with me. Right, so penta means 5, like a pentagram has 5 points to it. So we use mono, di instead of bi. So both di and bi mean 2. We're going to use di with the D as in dog. Tri, I think triangle, kind of know what that is. Tetra for 4. So sometimes you hear the word quad, like the quad on campus has 4 sides. We're not going to use quad, we're going to use tetra. So if you've heard of the game Tetris, this is where the blocks fall from the top of the screen and you fit the shapes together. Each of those blocks has 4 squares. And so that's why they call it Tetris, is that there are 4 squares that are put together either in a bigger square or in a long line or in an L shape, but it's always 4 squares. So tetra means 4. So the one quirky thing is that we don't use mono with the first one. And this is actually one you're probably familiar with. So the compound CO2, what is that? This one says SO2, but what would CO2 be? Carbon dioxide. So we don't say monocarbon dioxide, we just say carbon dioxide. So here we say sulfur dioxide, right? So there's one other rule that I didn't write out here. What am I doing to the second element? First element, I'm just using the name that's on the periodic table. What do I do to the second element? Yeah, you add IDE, and actually you change the ending. So we don't see oxygenide, we say oxide. We don't say nitrogenide, we say nitride, chloride. Okay, so you take off the last part and we say ide. Okay. Let me see. This is just a reminder of where those metals and non-metals are. So on our periodic tables on the wall, the green and the blue are in this region 5. Those are our non-metals, okay? If it has anything in red or brown, we don't use these naming. One exception is way over in the corner there, the green element. What is that element if you look up? Hydrogen. Hydrogen is always going to violate our rules. It is always going to be our problem child. So anytime I tell you something that is a rule for the periodic table, I'm going to say except for hydrogen. Hydrogen is the only one that is on the left side. All the others are on the right. Okay. Any questions? All right. Well, have a good weekend. I encourage you to check out the Festival of the Horse. There'll be lots of food trucks and vendors and things. And I'll see you on Tuesday.